If you're like me, you're sitting in a computer engineering class and you're completely lost. So what we're both going to do today is just start from the very beginning. So the very beginning is binary, and pretty much everybody's heard of binary, but what is it? Is it just ones and zeros? And if that's all it is, how do computers run off of it? And to be able to understand that, what we're going to have to do is talk about logic gates. What are they? What do they do? And when do we use them? And today, I'm going to explain all of that for your sake and for my own while I'm in these classes with Minecraft. So what's binary? Well, binary is a number system. Awesome. Numbers. Who could have guessed that? So what? Well, number systems are actually kind of cool. And there's a lot of them. It's not just binary. In fact, we use one. We use the decimal system for pretty much everything we do, whether that's math or money or whatever. We use the decimal system. But there's a whole lot more. There's octal, there's hexadecimal, and there's basically an infinite number of these systems depending on how many symbols you carry around in your pockets from time to time. And to explain what I just said, I need to show you how this all works. This is a decimal number represented visually. Might not look like it, but it is. And right now it's at 0. But when we add blocks, each one of those blocks is 1, 2, 3, 4, 5, 6, 7, 8, 9 respectively. But something interesting happens when we go over 9. When we do that, we have to make another box, add a block into it, and reset the original box to 0. This is called overflow. Overflow happens once we pass the available memory, or in this case, available space, and have to add another space. In decimal, it looks like this. Now that I've shown you how decimal works, binary is going to be a lot easier to understand. Unlike decimal, binary only goes up to a value of 1 before it overflows. So that means you go from 0 to 1 to 1 0 to 1 1 to 1 0 0 and so on into infinity. So that's how you represent numbers in binary, which is cool if you're doing math, but today we're not going to be doing math. What I want to show you is how computers take those zeros and those ones and use them to make decisions. And the way they do that at the most basic level is with logic gates. If you Google what a logic gate is, the AI overview will tell you a logic gate is a fundamental physical device implementing a Boolean function acting as the building block for digital integrated circuits. Those are really big words for Elmo. What that actually means is that a logic gate is the absolute most basic component to a digital circuit. And it will take those ones and zeros that we just talked about and perform a specific function based on what ones and what zeros it's getting. And since that's clear as mud, how about I just show you these gates and what they do? The first gate being built right now is the NOT gate. This is the simplest logic gate because it only needs one input to perform its function. The function the NOT gate, also known as an inverter, performs is taking a signal and inverting it. In the case of redstone, powered on represents a 1 and off represents a 0. You can see that when the lever is switched on, the lamp on the other side of the NOT gate turns off and vice versa. Next up is the OR gate. This is the next simplest gate to explain and to make. What it does is it takes 2 or more inputs, and if there is even just a single one, it will output 1. In the case of redstone, if there's power coming from either lever, the lamp will turn on. Now this is actually a good time to pause and explain truth tables. Truth tables aren't very complicated, but they can get a little tedious depending on how many variables you have. So to make this easy, let's just use that OR gate I just explained with its 2 inputs to go over the truth table for that. So we'll start out with a chart, and on this chart on the left side we have our inputs. We have every possible combination of those inputs that we can have. And then on the right we have every possible outcome or output for each one of those combinations of inputs. So as you can see on this chart, on the left we have 0 0, 0 1, 1 0, and 1 1. And on the right we have 0, 1, 1, and 1. Now this is a truth table for the OR gate. Keep that in mind. This only has 2 inputs as well. OR gates can have more. And in a lot of cases you actually use the truth table to design the circuit. So basically what I just did was backwards. And as a fun little side quest thing, I want to show you what an OR gate looks like in real life. So I have made this circuit here, and let me demonstrate what it does. So if we power it on, you'll notice that LED right there isn't powered on. But if I press this one, we'll call this input B, it turns on. If I press this input, which we'll call A, it turns on. If I press them both, it still turns on. That's how an OR gate works. Okay, now that I've talked about truth tables, let's go over the last basic logic gate. After this gate, everything I'll talk about is just a derivative of what I've already covered. This gate is the AND gate, represented by this symbol. What it does is take two or more inputs and determine if all of them are a 1. If all of them are 1, then it returns a 1. Unlike the OR gate, however, the AND gate will not return a 1 if any of the inputs are a 0. This is demonstrated here with this redstone circuit. Now that I've explained the basic gates, we can talk about their derivatives and how they differ from the original gates. The first of these gates is the NAND gate. The NAND gate is represented by this symbol, and functions just like an AND gate with a NOT gate slapped on the end. You can visually see that in this redstone example. It's literally just an AND gate and an inverter. Because of this, it will do the exact opposite of the AND gate, only returning 0 when both inputs are 1. And that's the only AND gate derivative that I've got. So let's move on to all the OR gate derivatives. And let's start with the NOR gate. The NOR gate, just like the NAND gate, is an OR gate with an inverter slapped onto the end of it. So that means it will produce the exact opposite outputs that an OR gate would give you. And after that, we've got the XOR gate. This gate is actually really interesting because it will only produce an output of 1 if only one of the two inputs is a 1. So that means if both inputs are 1, it's going to produce a 0. If both inputs are 0, it's going to produce a 0. But if A is 1 and B is 0, then your output is going to be a 1. The last OR gate variant that we're going to talk about is the XNOR gate. This gate is an inverter slapped onto the end of an XOR gate. Who could have guessed that? So basically, that means when both inputs are 0 or 1, it's going to output a 1. But when only one input is a 1, then it's going to output a 0. So that was a lot of yapping. How about I show you how we can actually make these work in Minecraft? So here's a really simple example of an AND gate being used in a piston door. So you can see that in order to open this door, you can't just do one of the levers, you have to use both. In this next example, we're going to be looking at a piston door with an OR gate. So you notice when I pull one lever, the door opens. I pull the other lever, the door still opens. And even if I pull both levers, the door will still open. So that's just another example of how an OR gate works. Alright, congratulations, you've made it to the end of the video. You've listened to me yap about binary and how it's a number system. I've explained number systems, kinda, and I've taken you through the basic logic gates. NOR, OR, AND, NAND, NOR, XOR, XNOR, and I've told you what they do. Personally, I'd love to go over the uses of gates like XOR in a video on half, full, and 4-bit adders, but I'm only going to subject myself to that if somebody other than my mom watches this video. So if you want to see that, be sure to let me know in the comments, and I'll get after it. And finally, I just want to say thank you for watching. Thank you for taking the time to watch this video, and I hope you were able to learn something from it. I definitely have learned a lot, not just about logic gates, but also about how to edit this video while I've been working on it. So it's been a really great project. And I'll also leave some links down below if you want to learn more about logic gates and about number systems. And I'll also link the website I found the Redstone Logic gates on, so be sure to check that out. Otherwise, thanks again for watching, and we'll see you in the next one.